Hello everybody, this is the solutions video for the Exam 1 review packet. I recommend that you use this video to check your answers for the review packet, so you can just scroll through the video, pausing, looking at the answers, seeing if you have the right stuff. But if you see that you have a wrong answer, then I would recommend that you back up and watch that portion of the video so that you're getting the explanations and not just seeing the answers. I don't recommend that you just fill in the packet by watching the videos. It's better to practice it on your own and then check your answers. That'll do better for you getting ready for the test. All right, let's jump in. So the limit as x approaches -1 from the left. We come to this function, we move along from the left-hand side, approaching -1, coming on this branch towards that solid circle, which has a height of 3, so that limit would be 3. Looking at the limit as x approaches -1 from the right, we're coming on this branch, getting close to the -1 from the right-hand side, approaching this open circle, which has a height of 2, so this limit would be 2. The next question is, what's the overall limit as x approaches -1? So because the limit from the left and the right do not agree, that would be does not exist, or we can just put DNE for that. All right, continuing along, the limit as x approaches 1 from the left-hand side, so now we've moved over to this portion of the graph. Approaching from the left is coming up this way to the open circle, approaching a height of 4. If we approach that 1 value from the right, we're coming from here towards that open circle, but still towards a height of 4. And when they ask us about the overall limit right here, because the limit from the left and the right match, that's going to be what the overall value is as well. It's worth noting that f of 1 is 5, but remember the limit isn't concerned with the actual value of the function, but just what we're approaching as we get close. All right, so let's look at that final possible interesting number over here at 3. If we approach that from the left-hand side, we're coming on this, and it looks like we're heading downwards, so we'd say that limit is going to be -infinity. And then as we approach that same number 3 from the right-hand side, now we're coming this direction, and that one is going up, so we're going to say +infinity for that one. And then because the limit from the left and the right do not agree, the overall limit does not exist. All right, and then the final thing they want to know from us is to look through and see if there's any x values where the function has a discontinuity, and if they do, they want us to justify our answer for why we're calling that a discontinuity using the continuity checklist. So, thinking about it just from the kind of intuitive point of view for continuous, as we come along here, if we were tracing this over, we'd have to pick up our pencil and jump down here. So when you have to pick up the pen or pencil to draw the graph, that would be a discontinuity. Here we have a hole, so if we were drawing it, we'd get to here, jump up, do the dot, and then come back down, so that's also a discontinuity. And when we come to 3, we have to pick up and go over here, and so we get a discontinuity. So it looks like the discontinuities are happening at x equals -1, x equals 1, and x equals 3. All right, so now let's make that list of discontinuities and justify our answers. So again, the 3 discontinuities appear to be happening at -1, 1, and 3. So x equals -1, x equals 1, and x equals 3 are the 3 spots that we're concerned with. So going back, at x equals -1, the problem was the issue of the limit from the left and the right not being the same, which caused the overall limit to not exist. So we can say the reason for the discontinuity at x equals -1 is that the limit as x approaches -1 of f of x does not exist. So that violates the continuity checklist. Going to x equals 1, the issue there is the limit does exist, it's 4, but it's different from the value of the function. So that's what we would list as the problem. The limit as x approaches +1 of f of x does exist, but it is not the same as the value at f of 1. Again, the limit is 4, value of the function is 5, so those are different. And at x equals 3, we've got the limit actually not existing because -infinity and an infinity answer are a type of does not exist, and the function's not defined either, so we've got like violations on every front at 3. The easiest explanation to give for why we have a discontinuity there is that f of 3 is not defined. All right, moving on to number 2. They want us to sketch a possible graph of the function f that satisfies all of the properties below and avoid any unnecessary discontinuities or complications when we draw that graph. So the first thing I want to do is make some notes about what's going on that involves infinities, because those usually create asymptotes. So right here we have the limit as x approaches plus or minus infinity is 1. If you talk about the limit as you go to plus or minus infinity and you get a number, that's creating a horizontal asymptote. So we have a horizontal asymptote of y equals 1. So that'll be something we want to draw in. And then also looking at where the limit turns out to be infinity. As we approach -2 from the left and from the right, we get infinity type answers. So we have a vertical asymptote at x equals -2. And then as we approach 0 from either direction, we get infinity. So that's another vertical asymptote at x equals 0. And then f of 3 equals 1 is an ordered pair on our function, saying if we put in 3, we get out 1. So that's all information I want to make sure makes its way onto that graph. So we'll start by setting up axes on here. So bring in a straight edge to draw good lines. I'll just go center, center. So we've got our x-axis and our y-axis. We want to think about scale, meaning can we number 1, 2, 3, 4, or do we need to go 3, 6, 9, or 10, 20, 30? If you look at all the numbers involved, 1, -2, 0, 3, 1, none of them are big numbers. So a scale of 1, 2, 3, 4, 5 is fine. Just got to number enough so that people can tell what the scale is. So I'll just put the 5s on here. Both positive and negatives. And then we want to start adding the information from over here and then make sure we got everything else incorporated as well. So the y equals 1 is a horizontal asymptote. So at a height of 1, we have a horizontal asymptote, so I'll draw that in. And then vertical asymptotes at x equals 2, so left 2. And then at x equals 0, so that's actually on the axis. I'll draw it just a little bit to the side, just so we can see the dashed line, but it's really on the axis. And then we're going to go through the point 3, 1, so over 3, up 1 is going to be a solid circle. All right, so we want to start drawing the graph. If we go over to this side, we know that as we approach -2 from the left-hand side, we're going to positive infinity, so that's an upward direction, like this. And then we know we have a horizontal asymptote here, so I'm just going to bend that function around so that it starts approaching the horizontal axis. And then let's see what's going on the other side of this vertical asymptote. As we approach -2 from the right, we're going to negative infinity, so coming down this way. And then as we approach 0 from either side, we're going to infinity, so that would be upward arrows here. And then we just want to connect that, so not sure exactly what it looks like, but just kind of do a smooth connection there. And then we've got to deal with this side over here on the right. And we've got some limits going on that we haven't talked about yet. So the limit as x approaches 3 from the left is 2. So if we're approaching this line of 3 coming from the left side, we get a height of 2. We know that can't be a solid circle because a function can't have two solid circles at the same place. So I'll do an open circle there. And if we approach from this value of 3 from the right, we get a height of 4. So that would be here. So this is probably the easiest thing to draw in. As we come to this side, we got to go up to that point. And as we go to the other side, we have to approach this horizontal asymptote because that was on both plus or minus infinity sides, so something like that. So the only thing that's left is the question of where do we go from this dot. So that has to do with what happens as we approach x equals 0. And as you approach 0 from either side, you're going up to positive infinity. So I'll just draw something that kind of curves and goes up. So I think we've got it. I just want to run through and check everything. As x goes way to the right or way to the left, are we approaching 1? Yes. As we approach 2 from the left-hand side, are we going up to infinity? Yes. As we approach 2 from the other side, are we going down? Yes. 0 from either side, up to infinity? Yes. The limit as we approach 3 from the left is going to 2. From the right, we're going up to 4, but actually at 3, we have a height of 1. So it looks like we've ticked all the boxes there, so there is a reasonable graph for that function. All right, moving on to number 2. They want us to use the TI-84 to verify that this inequality seems to be true, and then assuming that that is true, use the squeeze theorem to show or to find the value of the limit as x approaches 0 of sine x over x, which turns out to be a very important limit for us later on in the chapter, and they want us to show the work for the limit. So first let's go to the calculator part. We want to show that the sine of x over x is in between cosine of x and 1 over cosine of x. So I already went ahead and entered those three functions in, kind of in order from left to right, so I have the middle one as the second function. What I saw people do in class with this is when they went to graph it, they just did the standard window of negative 10 to 10 and negative 10 to 10. So there's our first function. And notice the second function as it starts drawing in, it seems to be crossing the first one, which isn't good for like it always being in between the left function or the first one and the last one. But remember, when we're doing a limit as x approaches 0, we're actually just interested in what's going on close to 0. So we're going to look at this picture and make sure that inequality seems to be true when we're close to 0. And then the other thing I want to do is look at the height. It looks like those are hitting somewhere around 1. So I'm going to change my window settings and just go from negative 1 to 1 so that I'm closer to 0. And for my heights, I'm just going to go from 0 to 2, so I'm kind of looking closer at where it seemed like those were going. So now I'm hoping, now that I'm closer to 0, that when I see the first function, second function, and third function get drawn, that the second one is always in between the other two. So let's take a look. There's our first function. Here comes the second one. That seems to be over, getting close there, but it still seems like it's, well, it's hard to tell if it's over or not. And then the last one seems up. So off to the left and the right, it seems like the second function's in between. If you want to get a sense of that closer where they seem to be blending together, if you hit trace and you go over just a tiny bit, like x equals negative 0.02, here's cosine of x as our first function. The y value is 0.99977. The next one is 99992, so that's a little higher. And then the third one is 1.0002. So it does look like the second one is in the middle of the other ones, even though they're very close together and almost seem to be the same in terms of the picture. All right, so let's go ahead and take it that this inequality is true, at least in the neighborhood of x equals 0, which is what we're interested in. And then let's show our work for finding this limit. So what I'm going to do is just take the limit as x approaches 0 of all three parts of this inequality. So I have the limit as x approaches 0 of cosine of x is less than or equal to the limit as x approaches 0 of sine x over x is less than or equal to the limit as x approaches 0 of 1 over cosine of x. And now what I want to do is just start evaluating left, right, and then hopefully middle for this. So our kind of goal, our hope, is that we can evaluate limits by just plugging in. And if we have continuous functions, we can do that. And we have a theorem that we've already gone over that said cosine is continuous. So as long as cosine is defined at 0, I can plug into it. Cosine of 0 is defined and is equal to 1, so that would be the limit. If you try and plug in here, you actually get sine of 0, which is 0, over x, which is going to 0, so 0. So 0 over 0, which is undefined. So I'm just going to leave that as a limit. Apparently we can't get that answer by just plugging in. So I'll just copy it again. And on the other side, here we have a constant function on the top and then a trig function on the bottom. So as long as plugging in doesn't create a 0 denominator, we can do that because these are both continuous functions. And when I plug that in, I have 1 on the top and I have cosine of 0, which is 1 on the bottom. So the answer on the left was 1, the answer on the right was 1 over 1. So by the squeeze theorem, the limit in the middle must be the same. So by the squeeze theorem right here, we know that the middle part has the same limit. So the limit as x approaches 0 of sine x over x is equal to 1. And again, that is going to be an important trig limit for us to know as we move on in chapter 3. All right, moving on to number 4. Determine whether or not the following statement is true and then explain why or why not. The function f of x equals the absolute value of x minus 2 is continuous for all x. Therefore, it is also differentiable for all values of x. So we know that if a function is differentiable, that it's continuous. So now they're trying to turn that around and saying, if we know that's continuous, does that also mean we know it's differentiable? So we can get at that idea for, is it continuous, first just in a visual way. If I go into the graph menu and I graph y equals, let's see, we want to go into the math menu, number menu, absolute value, x minus 2. So that's the absolute value of x minus 2, and I just want to graph that in the standard window. And we see it does look continuous, the V shape that you're used to with an absolute value function. But is it also differentiable? Well, there's 3 things that make things not be differentiable. A continuity, a discontinuity, which this does not have, a vertical asymptote, which it doesn't have, but also a corner, and it looks like we have a sharp corner at x equals 2. So just real quick, I copy that sketch over. So 1, 2, 1, 2. So we have this graph that kind of looks like this for this function, has a corner right here. So this is continuous everywhere. So continuous for all x, but not differentiable at x equals 2 because there's a corner there. So what does that mean about their statement? Since we've shown this part doesn't work, we can say that overall their statement was false. And there's our why not. All right, moving on to number 5. They want us to evaluate each of the requested limits and show all of our work. So if we look at this first one with the limit as x approaches 4, we should be able to see right away plugging in is not a viable option, because if you plug a 4 into the denominator, you get a 0. So we'll use our standard ploy of trying to factor and see if we can get that x minus 4 to cancel. So we have the limit as x approaches 4. There's an x in every term in the numerator, so we can factor out that GCF of x. Reduce all the x's on each term by 1. And then we still have the x minus 4, and now we have a ax squared plus bx plus c type. So we're going to try and factor that one by thinking of 2 numbers that multiply to 12 and add up to -7. So x minus 3, x minus 4 should do that, because -3 times -4 is positive 12, and -3 plus -4 is -7. And then we have the x minus 4 on the bottom, and then that's what we were hoping for, that we could get that factor to cancel so that we could then plug in. So now we have just the limit as x approaches 4 of x times x minus 3. So plugging in, we get 4 times 4 minus 3, which is 4 times 1, or just 4. All right, as you may have noticed, the black pen was dying, so it's out, blue's in. Continuing on to part B, we want to look at the limit as x approaches 1. And if you just try and plug in, we get 1 minus 8, which is -7, plus 7, which would be a 0. So plugging in isn't going to work, so we're going to try and factor. One of the things I like to do is have these in descending order, and one way to do that is to factor out a negative. If you have a subtraction and you factor out a negative, it reverses that subtraction. It's kind of a 2-step process if you go through it all, but that's the kind of net effect. And we are still taking a limit, so let's don't forget to write that. And then on the denominator, we can start trying to factor that one. It's ax squared plus bx plus c type, so we need 2 numbers that add up or multiply to 7 and add up to -8. would be -1 and -7. Two negatives to make the positive on the 7 and to add up to the -8. And then continuing on with the factoring process, still a limit. At that negative up top, we have a difference of squares, so x minus 1, x plus 1 for the factoring. And that's good news because we get a match with that x minus 1 that's in the denominator, so that can be canceled off. And now the problematic spot where plugging in a 1 made a 0 denominator has gone away. So we can start evaluating the limit by plugging in. So we have that negative. We're plugging in a 1, so we get 1 plus 1 up top. And in the bottom, we get 1 minus 7. So that looks like -2 over -6 or +3. So there's our limit there. All right, let's have a look at C. Oh boy, looks like we've got a complex fraction. Can we just plug in and have it be really easy? No, because if you plug a 0 in for h, you get a 0 denominator. So plugging in immediately is not going to work. So one trick when you have the complex fraction is to try and simplify the complex fraction, see if that helps you to be able to cancel that h. So these are two separate factors. It looks like they have 5 in common, but 5 is actually a term of this denominator, not a factor. So the least common denominator there is 5 times 5 plus h. So I'm going to multiply the top by that, and I'm going to multiply the bottom by that also. And up top, we're going to hope for some cancellation, so still a limit. And when we multiply this first part right here, the 5 plus h's cancel, and what's left is the 1 and the 5, so 1 times 5 is 5. That minus sign I'm going to copy. When I multiply these two together, the 5's cancel, and I'm left with the 1 times 5 plus h, so -1 times 5 plus h. In the bottom, I don't actually want to carry out the multiplication. I just want to write it as all three of these things multiplied together. I want to keep that factored so this h is ready to cancel should an h show up as a factor in the top. So continuing on, the limit as, h approaches 0 of 5 minus 5 minus h all over h times 5 times 5 plus h. These two 5's cancel each other, which is good news because now it looks like we have a factor of h up top. Limit as h approaches 0 of -h, which can cancel with that h in the bottom, times 5 times 5 plus h. Those cancel. The problematic piece of plugging a 0 into the denominator and having it make the denominator 0 has gone away. So I can now plug in. Up top I just have that -1. In the bottom I have this 5, and I have that 5, and I have plus h, which is going to 0. Looks like we're getting -1/10 for that one. All right, on to the last one. This one looks kind of scary, I suppose, but it really is one of the simpler ones on this page. If you try and plug in at pi over 4, both sine and cosine are √2 over 2. So these two would cancel out because they're both the same value. So you'd get a 0 denominator if you try and plug in, so we can't do that. So we have to try and get that denominator to cancel, make that problem go away. And it may seem a little intimidating or scary because of all the trig functions, but if you look at the top, sine squared minus cosine squared falls into the a squared minus b squared sort of category. It's a difference of squares. So it's going to factor as a minus b times a plus b, where the a is the sine function and the b is the cosine function, because we have a squared or sine squared minus b squared or cosine squared. So the numerator, well, first root still a limit, so the limit as theta goes to pi over 4. And by the way, we don't care if the variable is h or x or theta. It's just a placeholder. So they use theta to remind us it's an angle, but it could be any variable, it doesn't really matter. But we have that difference of squares, so it's going to be a minus b, which would be sine theta minus cosine theta, times a plus b, same thing but with a plus sign, so sine theta plus cosine theta, And then over the bottom, which we're going to leave the same, except for that I will put it in parentheses. And by doing that, that makes it clear that we have a matching factor, which I can cancel. And remember, that was the problematic factor. That was the piece that was creating a zero denominator. Now that it's gone, we can try and plug in the pi over 4 for theta. So we get the sine of pi over 4 plus the cosine of pi over 4. As I mentioned a moment ago, sine of pi over 4 and cosine of pi over 4 are both root 2 over 2. So that gives us 2 root 2's over 2, and the 2's cancel, so we just get root 2. All right, there we go. Not so scary after all. All right, let's look at number 6. They want us to consider the function f of x equals 2x squared minus 10x plus 12 over x squared minus 2x, and find each of the following limits. Looks like we're looking at limits as we approach 0 and 2 and plus and minus infinity. So I assume that if we plug in 0 and 2, we get 0 denominators. Yes, 0 minus 0 is a problem. And 2 squared is 4 minus 2 times 2, which is also 4. So we're getting 0 denominators there. So to examine this limit a little bit better, it would help to factor this function. So let's come over here and do a little bit of work on this. F of x equals, there's a GCF of 2 in the top. So factor that out, I get x squared minus 5x plus 6. And then the bottom, I can factor out a GCF of x, and I get x minus 2. The numerator is an ax squared plus bx plus c type, so we can try and factor that. We need two numbers that multiply to 6 and add up to negative 5, negative 3, and negative 2 would get that job done. And then over the already factored x times x minus 2. And we do get this cancellation right here. And we get a simplified version of 2 times x minus 3 over x. Okay, so let's start looking at the various limits here. So the limit as x approaches 0 from the left of this function. Well, if I try to put in a 0, I do get something over 0. I get, let's look at it more carefully. I get 2 times negative 3, negative 6 over 0. If you're getting a constant over 0, this limit is going to either be plus or minus infinity. So to determine which one it's going to be, let's make a little chart and think about it. So what's going on as we approach 0 from the left in terms of signs? So we'd have 2, which is positive, times 0 minus 3, or you could pick a number on the left of 0, like negative 0.1 minus 3 is going to be negative. And then if you put that like negative 0.1 right here, you have a negative in the denominator. So overall, you got 2 negatives, 1 positive. The 2 negatives would cancel, and you would get a positive overall. So this is going to be positive infinity for that one. And then as you approach 0 from the right, same idea. Plug in something like 0.1. 2 is positive. 0.1 minus 3 is negative. And 0.1 itself would be positive. Here we only have one negative, so nothing cancels it out. You'd get a negative overall, but we know we have a constant over 0, so we're going to either plus or minus infinity. Since we know it's a negative sign, it must be negative infinity that we're headed to. All right, we'll verify that in a minute with the graph just to make sure that our logic is good. And then how about as we approach 2? Well, that one is not going to be a vertical asymptote because the x equals 2 factor canceled, so that's going to be a hole in the graph. So now if we look at this simplified version, plugging in 2 does not create a 0 denominator. So if we want to think about the limit as x approaches 2 from the left or the right, we could just plug into that and see what we get. So I don't really want to call this f of x because it's a simplified version of f of x, but if I look at plugging 2 into there, I get 2 times negative 1 over 2, which looks like it would be negative 1. So that's going to be both of these spots. And then finally, what's happening with the limit as x approaches plus or minus infinity? Well, there you want to just look at the biggest powers, top and bottom. and they're the ones that are going to dominate this. So that limit ends up being the same as just looking at the limit as x approaches plus or minus infinity of just those biggest terms, 2x squared over x squared, in which case the x squareds would cancel and we would get 2. So as far as the graph goes, listing any asymptotes, I would expect the graph, because we have these negative infinities on the sides of x equals 0, I would expect that I have a vertical asymptote at x equals 0. Because when we go way out to the left or the right, we get a height of 2, I would expect a horizontal asymptote of y equals 2. Remember, asymptotes should be given in equation form. And then they want us to sketch it all, so let's try and do that first by hand, and then we'll verify it on the TI just to make sure that we've done a reasonable job and nothing's come out weird. All right, so let's see. I wrote y equals 0. Sorry about that. Y equals 2 is actually what we've got for our horizontal asymptote. So let's draw in our axes. We'll just go down the middle. We don't have any big numbers once again, so we don't have to worry about shifting this around or using an unusual scale. We can just go 1, 2, 3, 4, I think, in each direction. So let's see. Vertical asymptote at x equals 0, so just do that right along the y-axis. And horizontal at y equals 2, so we'll go 1, 2, 3, 4, 5, like we did before. 1, 2, 3, 4, and negative 5, and 1, 2, 3, 4, and negative 5. So horizontal asymptote at y equals 2. And then let's start analyzing all the different stuff that we have going on besides that. So we do have that hole, and let's see what's going on there. As you approach 2 from the right or the left, the height is negative 1. So over 2 down 1, that's where our hole in the graph is going to be. And then we have this horizontal asymptote and this vertical asymptote. And notice we are going down to negative infinity from the right-hand side. So I'm going to go bend that sort of like that. And then like this. And then on the other side of the vertical asymptote, we know we have the horizontal, and then let's see, we're going up to infinity. So we're going up this way, and then we're going to level off to that horizontal asymptote. And I think we're matching up with all the traits we found on that graph. Let's just give it a quick double check on the graphing calculator, see if it all matches up with the way we drew it. The hole probably won't show up, so we're going to have to trust our math on that part. All right, so let's go ahead and punch in the original function. When you have numerators and denominators with multiple terms, make sure you put those in parentheses. So 2x squared minus 10x plus 12 in parentheses for the numerator, divided by open parentheses for the denominator, x squared minus 2x. And then I went from negative 6 to 6 on my scale here, so let's make our window do that too. Negative 6 to 6, negative 6 to 6, and then I just slide this over a little bit and see if these two graphs seem to match up. All right, horizontal asymptotes don't show up, but it does seem like the graph is leveling off, and we do see it curving up and curving down. Again, you can't see the hole. I kind of mentioned that would happen. If we want to see the leveling off a little bit better and the climbing up to infinity a little bit better, we could go further out to the left and right. We'll go negative 16 to 16, and let's just look a little lower and a bit higher. And then you'll be able to see that flattening out for the horizontal asymptote a little better and the taking off up and down for the vertical a little bit better. But on the grid we did it, we still had basically the key features shown well. All right, moving on to number 7. They've shown us the graph of y equals f of x, and on the same set of axes, they'd like us to sketch a rough draft of y equals f prime of x. So one of the things that I want to use to get started is places where the derivative would be 0. The derivative would be 0 anywhere the original graph, has a horizontal tangent, and it looks like there's a horizontal tangent right here at this low point. So at that spot, the derivative, which we're going to draw in the blue here, would be 0. There's a high spot right there where we get a horizontal tangent, so that would be a 0 on the derivative. And here's another low spot where there would be a horizontal tangent, so that would be a 0 on the derivative. And then let's think about what happens in between these zeros. So from this low point to this high point, the function is climbing, which means that its derivative would be positive. All the tangent lines are positive. So if I draw something kind of like this, that represents positive slope all through this section. From that high point to this low point, the graph is decreasing, which means we'd have negative slope. So I could do a little loop similar to that here that's below the axis, representing those negative slopes. And then from here on, the graph starts to climb and getting steeper and steeper, so the graph goes up to the positive zone and goes higher and higher, representing steeper and steeper slopes. Before we get to this point, we're dropping into it, which means negative slopes. So all through here, you would have negative slopes that are getting steeper and steeper as that graph climbs up and up. So we don't know this one's equation, so we can't check it on the graphing calculator. But we do have zeros at all the places where we have horizontal tangents. We have positive for our curve whenever the graph is going up. And we have negative for the curve everywhere the graph is coming down. So that should be a reasonable rough sketch for the derivative. All right, here we go with number 8. We're evaluating each of the following limits. If they don't exist, we'll say so. And we're looking at limits as we're going towards plus or minus infinity. So I'm going to do the showing of the full work on all of these so we see what that process looks like. So just a reminder, when you're taking a limit as x goes to plus or minus infinity, what you want to do is divide by the largest power of x that's in the denominator among all the terms. So we're going to go 2x over x cubed, because x cubed is the biggest power in the denominator, minus x cubed over x cubed. Do that with every term on the top as well. So just plus 4x cubed over x cubed, and then plus 1 over x cubed. And then the limit as x goes to 0 of the simplified version of that, which would be 4 plus 1 over x cubed, and let's see, 2 over x squared, and minus 1. So now, as we take the limit there, as x approaches 0, anything that has a constant in the numerator and an x to a positive power in the denominator, as we take the limit, as x goes to infinity, those are going to go to 0. So we get 4 plus 0 over 0 minus 1, or just negative 4 for that one. And if we want to just apply the quick trick where we say all that really matters are the biggest terms in the top and the bottom. So if you cover up this piece and you cover up that 1, you have 4x cubed over negative x cubed. The x cubes would cancel, you get 4 over negative 1, which is negative 4. So the quick version checks out with doing all the work. Let's do that work again so we get used to it. What's the limit as x approaches negative infinity of this one? Well, the biggest power in the denominator is an x squared. So I'm going to divide every term, numerator and denominator, by x squared. And I'm going to speed this up a little bit and just go straight to plugging in here. Let's see, actually, no, not on this one. Let's keep writing. So the limit as x goes to negative infinity of, here the 2x's on the bottom cancel 2 of those on the top, but I still have a 3x. And then I have plus 8 over x here, a 2 here when the x squareds cancel, and then 7 over x squared. So if we look at what's happening, we're getting this goes to 0, this goes to 0, this goes to 3 times negative infinity, which would be negative infinity cut in half would still be negative infinity. when the numerator has a bigger power than the denominator, you're always going to get an answer of plus or minus infinity for that limit as you go out, just depending on what the sign of that remaining x piece would be. We tried to do the speed version and just said the biggest terms are what matter. If we cover that up, these two x's cancel one of those and we get 3 over 2 times x. 3 over 2 is positive times x, which is going to negative infinity, would go to negative infinity. All right, let's keep plowing along here. So take the limit as x goes to positive infinity this time. And the biggest term on the denominator is x to the 5th. So we're going to divide everything by that. So 2x to the 3rd over x to the 5th plus 7x to the 5th over x to the 5th, x to the 3rd over x to the 5th plus 9x over x to the 5th. I'm just going to jump right in here and start taking limits. This is 1 over x squared, so it goes to 0. This is 9 over x to the 4th, so it goes to 0. This is 2 over x squared when I reduce, so that goes to 0, plus the x to the 5th cancel, and I just get 7, so it looks like 0 over 7, or just 0. That's what should happen anytime the power on the denominator is larger than the power in the numerator. If you just paid attention to the biggest terms only, you have x cubed over 7x to the 5th, which is 1 over 7x squared, which is going to go to, let's see, yeah, it's just going to go to 0 overall. All right, and now let's look at our favorite kind, the square root kind. That's all right, though. These are easy as long as the limit doesn't go to negative infinity. Oh, that's where we're going, negative infinity. So why is that a trickier case? Well, because if x is less than 0, then the square root of x squared is equal to negative x. Sounds like we're saying that the square root of x comes out negative, but remember, if x is negative, then the negative of x would be positive. So we're making sure, actually, that our square root is producing a positive answer. So what we want to do here is think about what's the square root of x squared? It's x. That's the biggest power in the denominator. So we want to divide top and bottom by x, but we want the thing we divide by to be something that can move in as an x squared, and what would move in as an x squared is an x, but negative x. So we're going to take this one a little bit slower. We're going to look at the limit as x approaches negative infinity, and we're going to multiply the top by negative 1 over x, and we're going to multiply the bottom by negative 1 over x. And the reason we did the negative is because we want to take that negative x and move it inside of the square root where it will be an x squared. So up top, we end up distributing this. The x's cancel, we get negative 1, and then minus 1 over x. That's our numerator, still taking the limit as x goes to negative infinity. And then we're going to move that negative x inside as an x squared. So we're going to have 9x squared over x squared plus x over x squared. Then we're going to start plugging in. So up top, we have the negative 1, and then we have negative 1 over x, where x is going to infinity. So if you have a constant over an infinity, that piece is going to 0. And then in the denominator, we have the square root. These x squareds cancel, so the square root of 9. And then we have x over x squared is 1 over x, which is going to 0. So we have negative 1 over the square root of 9. So negative 1 over 3, or negative 1/3, is our final answer for that one. All right, moving on to number 9. Find the equation for the slant asymptote for this function. So first of all, how do we even know it has a slant asymptote? That'll happen anytime the largest power on the top is exactly 1 higher than the largest power in the denominator, which we do have here. And then if you want to figure out the equation of that slant asymptote, what you need to do is do the division that's shown as a long division. So the numerator goes underneath 3x squared plus 2x minus 1 divided by 4x plus 1. To do the long division, take the first term underneath, divided by the first term out front, simplify that, you get 3/4 x. So that's going to be the first term of our answer. Multiply those together. 3/4 times 4 is 3, x times x is x squared. 1 times 3/4 x is plus 3/4 x. We want to subtract that from what's above. By design, these will cancel, so 3x squared minus 3x squared, that cancels off. 2x minus 3/4 x, that's 8/4 x minus 3/4 x, so that'd be 5/4 x. And then bring down the minus 1, and then do the long division again, so we have 5/4 x divided by 4x. The x's cancel, and multiplying top and bottom by 4, these 4's would cancel and we get 5/16. So that's the next term of our answer. Multiply those out. 4x times 5/16, that 4 cancels one of the 4's in the bottom, and we get 5/4 x, which is perfect because it matches that piece. 1 times 5/16 is plus 5/16. Subtract that from what's above. Didn't leave much room there, but that's okay. These cancel. And then we have minus 1 minus 5/16. But that minus 1 is actually minus 16/16. Minus another 5 would be minus 21/16. This piece doesn't matter too much because it goes up here as minus 21/16 over the divisor. And this piece right here, if you look at the limit as you go to plus or minus infinity, this piece goes to 0 because the denominator is going to 0. So your slant asymptote is y equals this piece. So we end up with a slant asymptote of y equals 3/4 x plus 5/16. All right, on to number 10, find the intervals of continuity for this function. So let's see, we've got kind of a divisor down here, so that can't be 0 or else we'd have a discontinuity. So if 2x plus 9 equals 0, which means 2x equals -9 or x equals -9/2, then we will get a 0 denominator, and that means the function's not defined there, so that's a discontinuity for sure. And then we've got a polynomial underneath a square root. So that is going to be continuous as long as it's not a negative for the polynomial. So to think about where the polynomial is greater than or equal to 0, we would write that down. 3x squared minus 7x minus 10 is greater than or equal to 0. We would factor that. 3x and x would get us the 3x squared. A little factoring trick I use when I have a number out front instead of just the 1 is I multiply these two together. That's -30. And I try and think of two numbers that multiply to -30 and add up to -7. So -10 and +3 do that. The product is -30, but the sum is -7. Whenever you can find two numbers that do that, those are your outer and inner products on the FOIL. So to get that 3 right there, if I put a +1, that would create the 3x for that 3. To get that -10, that would be 1x times -10. And check that real quick. 3x times x is 3x squared. -10 times +1 is -10. Outer is 3x, inner is -10x, and 3x minus 10x is -7x. So that is factored correctly. We get zeros for that when x is equal to 10/3 and when x is equal to -1. So what we do is we think about on the number line, see, -1 would be over here, 10/3 over here somewhere. And then what happens if you plug a number to the right of 10/3 in, like say 5? you'd get 15 minus 10, which is positive, times 5 plus 1, which is 6, which is positive. So positive times a positive, everything over here is going to produce a positive. And then what if you plugged in something in between like 0? So you get negative 10 times positive 1, which is negative. So everything in here produces a negative. And on the left, something like negative 2 would be negative 6 minus 10. That's a negative. Negative 2 plus 1, that's a negative. Negative times a negative would be positive. So remember, what did we want? Places where this was greater than or equal to 0? Equal to 0 at these points, and then greater than 0 to the right of there and the left of here. So where is this function continuous? Everywhere out here and everywhere out here except at x equals 9, negative 9 halves. So that negative 9 halves is out here somewhere, and that would be a hole. So it looks like our intervals of continuity would go from negative infinity to negative 9 halves, where that, it's not necessarily a hole, it's actually probably a vertical asymptote right there, but it's still a discontinuity. And then from negative 9 halves to negative 1. And then and that's included, but then all of a sudden the function's not defined because you get a negative under the square root until you get to 10/3. Then it's defined again and continuous from there to infinity. So there's our intervals of continuity for that one. All right, moving on to number 11, we're going to start thinking about the intermediate value theorem. So they want us to consider the equation x to the 5th plus 7x equals negative 11 and use the intermediate value theorem to show the equation has a solution in the interval from negative 5 to 4. So first of all, to use the intermediate value theorem, you need a function. So I'm going to let f of x equal the left side of that equation, which would be x to the 5th plus 7x. What's nice about that is that's a polynomial. So we can say that f of x is continuous over the closed interval corresponding to this one, which is negative 5 to 4. And we can say that because f of x is a polynomial. And to be able to use the intermediate value theorem, you need your function to be continuous on the closed interval that corresponds to this. And then you want this value you're trying to be equal to be in between the values of the endpoints. So let's find the values of those two endpoints. So first of all, f of negative 5, if you plug that into this function right here, so let's see what we could get for that. So we have negative 5 raised to the 5th. I actually should have put that in parentheses, but because it's an odd power, it doesn't matter. Plus 7 times negative 5 is negative 3160. And then we do the same thing for f of 4. So we take 4 and raise it to the 5th, plus 7 times 4, and we get 1052. And what's important, if we want to use the intermediate value theorem, is that these two values have that one surrounded. So we can say that f of negative 5 is less than or equal to 11 is less than or equal, sorry, negative 11 is less than or equal to f of 4. So negative 11 is in between these two values, f of negative 5 and f of 4. So we have a continuous function from negative 5 to 4. Negative 11 is in between f of negative 5 and f of 4. So the intermediate value theorem, or IVT, states that there is a solution. Well, it actually says there is a c, a variable c, in the open interval from negative 5 to 4, satisfying f of c equals negative 11. And then how does that do us any good? Well, just thinking about what does it mean for f of c to be equal to negative 11. Here's f of c, so f of c is c to the 5th plus 7x, so sorry, 7c. That's equal to negative 11. But what does that mean? That when you plug c into the original equation, it makes the two sides equal? That implies c is a solution. All right, so now they want us to use the TI-84 to approximate that solution to 4 decimals, because the intermediate value theorem can guarantee you that a solution exists, but it's not actually telling you what the solution is. So we're going to turn to technology for that part. I'm going to go into the graphing calculator and let y1 be the left side of the equation. So I'm going to let y1 be this x to the 5th plus 7x side, and y2 is going to be the other side of that equation, which is the negative 11. And if I find out where they intersect, that would be like finding a solution to this equation, and hopefully that ends up being between negative 5 and 4. So let's look at the calculator real quick. I went ahead and put those two functions in already. We can do a zoom standard, and we'll see the first function, the x to the 5th plus 7x. Then we don't see the negative 11, and that actually makes sense because the zoom standard only goes down to negative 10. So if I want to see that, I would change my window to go down farther. So instead of just going down to negative 10, I could go down to negative 20. And the other thing that makes sense to change is if we look at the interval we're working over, it's just the interval from negative 5 to 4. So why don't we only look from negative 5 to 4, because that's where we're really wanting a solution to occur. So here comes that first function again, and this time we will see the y equals negative 11 drawn in, and it does look like they hit each other. To figure out where they hit each other, you want to go into the calc menu, so I hit the blue second key first, and then choose intersect. And then they want to know, is that my first curve? Yes, so I just pressed enter. Is y2 equals negative 11 my second curve? Yes, so I just press enter. And then they want to guess at the point of intersection, so just move nearby. Make sure you don't write that number down. That's still, notice it says guess. But if you press enter one more time, it'll figure out precisely where that is, or at least to many decimals. They want us to give that answer to 4 decimals, so negative 1.206. There's a 3, but it's followed by an 8. So negative 1.2064. And again, to get that, I went into the calc menu and I used the intersect function. And to carry that out, you ended up having to press the enter button 3 times. Once to say yes to the first equation, once to say yes to the second equation, and then once to accept a guess. All right, there we go. All right, moving on to number 12, where they want us to give a formal proof that the limit as x approaches 3 of 5x minus 2 is equal to 13. And when they talk about a formal proof, they're talking about the epsilon and delta form of a proof. So we'll start off with a little bit of scratch work. So what you always want to do is start off with the absolute value of f of x, which is the inside part, minus the limit, which is the outside part. Set that to be less than epsilon and start to do algebra to try and get x minus a, or x minus 3, to be on one side and everything else on the other. So we have 5x minus 15 if we combine the like terms. We can factor a 5 out since that's positive. We can take it right out of the absolute value. And then divide both sides by 5. And we get the absolute value of x minus 3 is less than epsilon over 5. So this is the x minus a that we want to be less than delta later, so that suggests that this, epsilon over 5, should be our pick at delta. So now let's move over to the formal proof now that we've done our scratch work. So let epsilon greater than 0 be given, and then it's our job to choose the delta. So we pick delta equal to epsilon over 5. And then we want to show that if x minus a is less than our delta, that will prove that f of x minus L is less than epsilon. So suppose that we're dealing with an x such that 0 is less than the absolute value of x minus 3, which is less than delta. that would imply that the absolute value of x minus 3 is less than epsilon over 5. So I'm just kind of taking the right-hand portion of this, but substituting in the epsilon over 5. And then I'll multiply both sides of that by 5, so I get 5 times the absolute value of x minus 3 is less than epsilon. That 5 is positive, so I can just multiply that into the absolute value and get 5x minus 15 is less than epsilon. And then I can split that 15 up, kind of like we did over here, going backwards on that. So it's 5x minus 2, which is the f of x part, minus 13, which is the L part, but that still equals that negative 15 is less than epsilon. And then that is f of x minus L, so we have now shown that f of x minus L is less than epsilon. So we started out with x minus a is less than delta. We ended up with f of x minus L is less than epsilon, which is what we need to do to complete the proof. So QED, which means the quad era demonstrata, which means we have demonstrated it or the proof is finished. All right, moving on to 13. Consider the function f of x equals 3 times the square root of 5x plus 1. Use the limit definition of derivative to find f prime of x, and then simplify our answer. So we'll start off by writing that limit definition down. The limit of f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. Writing that out for this specific function means plugging that x plus h right there in place of that x right there. So that would be 3 times the square root of 5 times x plus h, and then plus 1 minus the original function, 3 times the square root of 5x plus 1 all over h. So it would be awesome if we could just evaluate that limit by plugging in h equals 0. That was supposed to be a 0, not an infinity. But you can't plug in a 0 there because you would get a 0 denominator. So for problems like this that have a radical, when you need to cancel that h but you can't right now, try rationalizing. That will often help. The other thing that would help, because we have this 3 out front on both of those, is let's factor that 3 outside of the limit, which again is h goes to 0, not the infinity that I wrote a minute ago. As we write this one down, I'm going to do just a little bit of simplifying. I'm going to clear those parentheses right there, and we get 5x plus 5h plus 1 minus the square root of 5x plus 1. Remember the 3 that was there we factored out front, and then that's all over h. And now we're going to do the rationalizing step. We're going to take this numerator and multiply it by the same thing but with a plus sign. So the square root of 5x plus 5h plus 1 plus the square root of 5x plus 1. And if we multiply the numerator by that, we also multiply the denominator by the same thing, so I'll copy that down here as well. And why is that beneficial? Because when we multiply by the conjugate, which is what we just did there, you end up getting an a minus b, a plus b situation, which results in an a squared minus b squared. So this is our a. If we square it, the square root and the square cancel. So our a squared ends up being just 5x plus 5h plus 1. And then minus b squared, we square this b, the square and the square root cancel, and we just get 5x plus 1. We do have to remember we're subtracting the whole answer to that, so we need to put that in parentheses to make sure that works out right. Our h was down there, and now we have this new stuff down there. Don't multiply that out, though. Just keep it in parentheses. Copy it over for now until we can plug in for h. And we can start doing that plugging in as soon as everything cancels in the numerator that doesn't have an h in it. And when we clear the parentheses, that is what's going to happen. So we get 3 times the limit as h goes to 0. We have, I'm going to just show this part. This minus 5x and that minus 5x cancels. And then we have 1 minus 1, so those are going to cancel. And we just have the 5h up top. And we have a whole bunch of stuff in the bottom that I didn't quite leave room for, so I'm just going to kind of cram it in here. But we've got the h out front, and then the parentheses and the square root of 5x plus 5h plus 1. I'll write this better on the next line, plus the square root of 5x plus 1. But the good part is these h's right there cancel. So we end up with 3 times the limit as h goes to 0 of just a 5 on the top now, and all this part right here is still on the bottom. So square root of 5x plus 5h plus 1 plus the square root of 5x plus 1. And now, because we canceled that h, plugging an h, a 0 in for h is not going to create a 0 denominator anymore. So we do that to evaluate. So we get 3 times 5. Here we get the square root of 5x plus 1, because if we plug a 0 in for that h, it goes away. And then plus this 5x plus 1 in the square root. So kind of looking at where that puts us now, we have the 3 times 5 is 15. And these are exactly the same, so we have 2 of them, so 2 square roots of 5x plus 1. So we're all the way done. We got rid of the h. This is going to be our derivative. So f prime of x equals 15 over 2 times the square root of 5x plus 1. That's a pretty messy one, but hopefully we got there okay. All right, on to number 14, where we're going to evaluate and simplify some derivatives. But at this point, we get to use the power rule, so hopefully these are going to go much quicker than that last one did. So we have the 3 is the power. We bring that down, times the 2/3, which is already there, and x to the power 1 less, or 3 minus 1, which would be a 2. Bring that 2 down, multiply it with the 7, 14, x to the 1 less, or to the first. For linear terms, you just get the coefficient because it's the slope, and then 13 is a constant, and pi to the 7th is kind of a tricky thing. It looks like a variable, but our variable we're differentiating with respect to is x. Pi is just a constant, so pi to the 7th is just a constant, so its derivative is just 0. These 3's right here cancel, and we end up with the derivative of x squared plus 14x minus 5. And we still have that 2 right there. The 3's canceled, but not the 2. So there we go. 2x squared plus 14x minus 5. On this one, we have a division, and we don't yet have a quotient rule. So if we want to take that derivative, we have to rewrite it so it's no longer a division. And one way to do that is to bring that x to the 7th up to the numerator, which will make its exponent negative. But then we can just use the power rule and say the derivative is 3 times negative 7, or minus 21, x to the power 1 less, and if we subtract 1 from the exponent, that would be minus 8. They do want us to simplify these answers. Answers aren't considered simplified if they have a negative exponent, so negative 21 over x to the 8th to make that a positive exponent again. All right, moving on to number C, we have a similar issue as we did here where we couldn't do division. When we have a square, we can't just use the power rule because this is an x to a power. And what that power of 2 really means is 3x minus 7 times itself, which is a product, and we don't have a product rule yet. So the way we handle this is to actually go ahead and do the squaring, which you could do by FOIL or by formula. I'm going to use the formula. When you square a binomial, you end up with the first term squared, 9x squared, minus the product of these two, negative 21x doubled. It's a minus 2ab in the formula, so that'd be minus 42x, plus the last term squared, which would be 49. Now we just have individual terms, and we do have a rule that says we can differentiate term by term. So just going through and using the power rule, bring the 2 down, you get 18x. Here you just take the coefficient, and the constant goes to 0. So 18x minus 42 for our derivative. And then finally, taking the derivative here of a quotient, but we can't do quotients, so somehow we have to make that go away. So what we want to do is split this up into two fractions. 4x squared over the square root of x, which I'll write as x to the 1/2, plus 9 over the square root of x, which I'll also write as x to the 1/2. And then we can simplify each piece of that, which will make it not be a quotient anymore. Not taking the derivative yet, that's waiting until we get this ready. We have x to the 2 minus 1/2, so that would be 4x to the 3/2. And here we just bring that x to the 1/2 up, which changes the sign of its exponent to negative 1/2. But now we can apply the power rule. So the derivative is now going to be taken, bring the power down. 3/2 times 4, 2 goes into 4 twice, times 3 is 6. So we get 6x to the power 1 less, which would be 1/2. Bring that 1/2 down, multiply with the 9, you get minus 9/2. Subtract 1 from the original power, you get minus 3/2. So this part's fine, but here we have a negative exponent, so one final step of simplification. We have 6x to the 1/2, and then we have minus 9 over 2, and I'm going to move this x to the negative 3/2 down, which will make it x to the 3/2. It'll change the sign when I move it down, and now I have a positive exponent, which is considered simplified. So there is that final answer. All right, moving on to number 15, where they want us to consider the function f of x equals 2x cubed minus 5/2 x squared minus 21x plus 42. Find and simplify the derivative. So that's going to be straightforward power rule stuff. So bring the 3 down, multiply with the 2 is 6, subtract 1 from the original power, that'll be a 2. Minus, bring the 2 down and multiply with the 5/2, and the 2's will cancel. We'll just be left with the minus 5, subtract 1 from the power. You get x to the first, or just x. Derivative of the minus 21x, it's a linear piece, so we just get the slope portion, or the coefficient, so minus 21, and the derivative of the constant is 0. So there's our derivative, nice and quick and easy. Find an equation of the tangent line to the graph when x equals 2. So the slope of such a tangent line comes from taking the derivative and plugging in the x value in question. So that would be 6 times 2 squared minus 5 times 2 minus 21, which is equal to 6 times 4 minus 10 minus 21. So let's see here, we got 24 minus 31 is negative 7. So that's our slope. And then to get the equation of the tangent line, we also need the y-coordinate that goes with this. So we need to know what f of 2 is. So f of 2 would be 2 times 2 cubed minus 5/2 times 2 squared minus 21 times 2 plus 42. I'm just going to put that into the calculator real quick. So let's see, we get 2 times 2 to the 3rd minus 5/2 times 2 squared minus 21 times 2 plus 42. Looks like we get equals 6. So now we have the slope of our tangent line, and we know that the x is 2 and the y is 6. So the slope using the point slope form will get us the equation. So y minus the y coordinate equals the slope, which was negative 7 times x minus the x coordinate. There's an equation right there. We could box that if we want to go to slope intercept form. We get y equals negative 7x plus 14 right there, and then add 6 to both sides. So that would make that plus 14 plus 6, so plus 20. So there's the slope-intercept form of the equation of that tangent line. All right, and then finally, for what values of x does the function have a horizontal tangent line? And show our work. So you get a horizontal tangent line anytime the derivative equals 0. So we want to set f prime of x equal to 0 from up top. We know f prime is 6x squared minus 5x minus 21. So we set that equal to 0 and try and solve. Hopefully we can factor that. It's going to be a trial and error type of factoring. Could be 6x and x, or 3x and 2x. I'm going to play my little number game here. So 6 times negative 21 is negative 126. Two numbers that multiply to that I know of for sure are negative 21 and 6, because that's how I got it. Those add up to negative 15. I want the sum to be negative 5. So I want numbers that are closer together. So let's see, there's a 3 in each of these. So there's a 9 that goes into 126. 3 goes into there 7 times, into there twice. So I think 9 times 14 will give us 126. But I need a negative, so I'm going to put a negative on the 14. So 9 times negative 14 is negative 126. Add them up, you get negative 5, which is the middle term. So these two right here are my outer and inner. So I know I have to use 3x and 2x now, because if I put a 6x right there, I'm not going to get a 9 or 14 by multiplying by 6. So I can get that 9 though by going 3x times plus 3. And I can get that negative 14 by doing 2 times negative 7. That might be a weird way of factoring that you haven't seen before. It's a nice little trick that I like though. Let's check to make sure it worked. 3x times 2x is 6x squared. Negative 7 times plus 3 is negative 21. You got plus 9 for the outer x, plus 9x, minus 14x. 9x minus 14x is negative 5x. So that is a good factoring. And then when do these factors equal to 0? When x equals 7/3, and when x equals negative 3/2 from this one. So those are the two x values where the derivative is equal to 0, and therefore also where we have horizontal tangent lines. All right, moving on to number 16, show which branch is being used for these limits. Consider this function that is piecewise defined. Find the limit as x approaches 0 of f of x. So if we're approaching 0 from the left, then that means we're smaller than 0, so that would be the cosine of x branch. So we're looking at the limit as x approaches 0 from the left of cosine of x. Cosine is continuous, so we can just plug into that, and cosine of 0 is 1. The limit as we approach 0 from the right means we're a little bit bigger than 0, so a little bit bigger than 0 would be somewhere in between 0 and 4. So now we're looking at the branch where x approaches 0 from the right, and we're looking at the middle branch, negative x plus 1. Plugging into that with the 0, we get negative 0 plus 1, or 1. So when they ask us what's the overall limit as x approaches 0, since the limit from the left and the right were the same, the overall limit is that value of 1. Moving on and doing the same thing for 4. If we approach 4 from the left, so smaller than 4, something a little smaller than 4 might be like 3.9, so that would be in here. So we'd be using that middle branch again. So this is the limit as x approaches 4 from the left of negative x plus 1. If you plug in the 4 to that, which you can do because it's a polynomial, it's a linear, we end up with negative 4 plus 1, which is negative 3. Approaching 4 from the right means greater than 4, so we're looking at the limit as x approaches 4 from the right using this branch, x squared minus 7x plus 8, still a polynomial, so we can still plug in 4 squared minus 7 times 4 plus 8, and let's see, what is that? 16 minus 28 and plus 8 is negative 4. Notice the limit as we approach 4 from the left and the right do not equal each other, therefore the overall limit does not exist. And so now they want us to determine the intervals for continuity. Well, notice that at 0, well, first of all, these three functions all individually, if we look at the branches, they're all continuous functions. So we know they're continuous except for at 0 and 4 because of the branches themselves are built from trig functions and polynomials. Where we might get discontinuities is at these transitions between the different definitions on the different branches. But at 1, the limit from the left and the right are the same and equal to the value of the function. Actually, I'd like to say it's equal to the value of the function, but looking at this more closely, notice that at 0, this is x less than 0 and this is x greater than 0. There is no definition for what the value of the function is at 0. So f of 0 is undefined, which means we have a discontinuity there. So that's tricky. So even though the limit exists, the function's not defined there, so we have a discontinuity. Now, f of 4 is defined because there is an or equal here, so f of 4 is this -4 value. However, the limit doesn't exist there because of these two branches, so that means we have a discontinuity. At x equals 4. So x equals 4 here, x equals 0 there. So the function is continuous everywhere except for at those endpoints. So the intervals of continuity would be from -infinity to 0, and from 0 to 4, and from 4 to infinity. And then finally, number 17, consider the function f of x equals 2x to the 7th minus 3x to the 5th plus 5x to the 4th minus 13x squared plus 8. Find f for x. So first question is, what does that mean? And that parentheses number there tells you what order derivative you want. So they want us to find a fourth derivative of this function. And we just do those in order. We find the first derivative, then we take the second derivative by taking the derivative of the derivative, take the derivative of the second derivative to get the third, take the derivative of the third derivative to get the fourth derivative. So just going through those in order, using the power rule a lot. F prime of x, bring the 7 down, we get 14x to the 6th, subtracting 1 from the previous power. Bring the 5 down and subtract 1 from the power, so minus 15x to the 4th. Bring the 4 down, subtract 1 from the previous power, so plus 20x to the 3rd minus 26x. Derivative of a constant is 0. Forgot my x there. So there's the first derivative. Second derivative comes from just taking the derivative of this one. Bring the 6 down. Getting a little messier with the numbers now. So 6 times 14 is 84. Subtract 1 from the power. 4 times 15 is 60. Subtract 1 from the power. 3 times 20 is also 60. Subtract 1 from the power, and this is a linear, so just minus 26. Third derivative, take the derivative of the second derivative. So 5 times 84, I believe that's 420, yep. Subtract 1 from the power. 3 times 60 would be minus 180. Subtract 1 from the power. 2 times 60 is 120. Subtract 1 from the power, and the derivative of a constant is 0, so that goes away. And then finally, the fourth derivative, we usually stop writing the primes by then. And derivative of this one, so 4 times 420 should be 1680. Subtract 1 from the power. 2 times 180 is minus 360. Subtract 1 from the power. This is linear, so the derivative is the coefficient, which represents the slope in a linear case. And there is our fourth derivative. So a little tedious to go through the derivative of the derivative of the derivative of the derivative, but we get there, and it's just power rule the whole way. All right, hopefully you found this video helpful for your review.